Hi, this is Russ at DevotedGolfer.tv. It's the 2016 PGA Merchandise Show, and I'm here with Bennoit Vincent. I get that right?
That's correct, Russ.
And Bennoit is the Senior Vice President, give me the title, because I'm going to blow it one more time.
I'm just a Senior Executive Vice President of TaylorMade R&D Department.
Okay. That's a mouthful. That pretty much means you're in charge of
Designing golf clubs.
designing, manufacturing as well?
As well, yeah.
Designing, manufacturing, and how long have you been doing this?
26 years now.
26 years at TaylorMade. Yeah.
It's has been a wonderful journey. The first 5-6 years were in France, and I came to the United States 20 years ago.
Yeah.
It's wonderful.
And so how did you get started in golf?
Actually, I was working as a research engineer in France and for aerospace mainly, and then I transferred to golf pretty much in the late 80s when TaylorMade was looking for engineers that were specialized in designing and computing the performance ahead of time before you make any physical parts. Can you predict how the golf club is going to behave? And they needed engineers that knew how to do that, and that was typical of what you would find in the aerospace industry.
And that's 26 years ago, right?
Yeah.
I mean, we now look at golf and we think about technology, but 26 years ago, friends and family must have thought that this was kind of an interesting place for somebody that had an advanced degree in your PhD in
In mechanical engineering.
Engineering.
So
So 26 years ago, a mechanical engineering PhD goes into the golf business. What did the family think of that?
That was unusual. I mean, there was doubt about in the family to spend all this money and energy to get advanced degree and use it in golf. But back then golf was a lot of trial and errors.
Yeah.
There was a lot of art that went to golf clubs and a little bit of science, but way less than it is today. I think that's what we did the last 25 years. We brought to golf a lot of scientific methodology and techniques in order to advance performance.
Yeah, and so TaylorMade's been doing this for 26 years. It's not like you showed up 2 years ago and decided that you were going to be a technical leader in the business.
Oh, you're right. You don't become a technical or leader in a business when it requires that level of advance in performance overnight. I mean, it is really a building up acquisition year after year, and then that's when you can do every year way much better than last year. And when you do that, 20 years in a row, you design the leading project.
Yeah, you end up with a very interesting product. So I met a engineer the other day in your booth who's an acoustic designer, came from the aerospace industry, and his specialty is vibration and acoustics. How does vibration and acoustics influence the perception that a golfer has with a club in his hand?
Yeah, the performance of a golf club is made not only about the trajectory you produce with your golf club, but it's also the sensation that you're feeling at impact. And those sensations came in typically two forms. One, it's what you feel through your hands and what you hear through your ears. And these two signals actually contribute to the perception of the golf club at impact. And it is very important, but it's extremely complex because it has to do with something that is very subjective, that is human perception. And we need to understand the complexity of that phenomenon. And it takes the engineers, acoustic engineers actually, to figure this one out.
So is it the timing of the sound? Is it the amplitude of the sound, or is all of the above?
Actually, there are three major components. Yeah, it's the amplitude, the duration of the sound. So typically on the golf club, the sound lasts 0.23 seconds. So knowing that a swing is a second and the impact, it's 0.5 milliseconds. So it lasts a little after the impact. The second contribution is how loud is the sound. It could be very loud, it could be very, And then the last piece is what we call the frequency content, which is a high pitch, is a low pitch. And those three components together gives you the quality of the sound. Yeah?
So how do you discover that? You bring people in and you test them and
Oh yeah. You hit the ball, and you put microphones around the golf clubs, around the golfer.
Mhm.
I would say you capture the sound that is produced at impact,
Mhm.
so you get what the golfer is hearing, and then we analyze the signal, and we find all the components that I just gave you, and we see if it's too loud, not enough. What's the content of it? Yeah, we break it down to understand what it is, and then of course we ask the golfer what he feels through his hands, and we try to understand. And then guess what? This process that's the process of testing, but we also try to design at the beginning, because we don't want to go for many trials and errors. That would take forever to design a good golf clubs. So we're trying to predict actually this quality of the feel at the design level. So we have computers and softwares. When we're done entering the shape of our new product, actually we're computing what you're going to experience. We're computing the sound of the product before we make a prototype. And so we can hear virtually, numerically, if you want, the sound of the product before we hear the real sound of the product in the real test.
And that's why you have acoustic engineers at staff.
Exactly. Right.
Yeah. Launch angle. Let's talk a little bit about launch angle.
So with the M2 irons, we were trying to achieve a great distance and a high peak trajectory. And the way we did that is by using a flexible speed pocket here. It generates more launch angle than what the loft would do. So 2-3 degrees more launch angle than the same iron without the speed pocket.
So the speed pocket is putting the ball up
in
higher.
the air.
Yeah.
It launching higher than what the loft would do.
Okay.
Without, and then the second portion is, because we relocate the weight as low as we could, the center of gravity goes, trajectory of the center of gravity goes below the ball and is pushing the ball even higher.
Up. Yeah.
So we get two mechanisms that pushing the ball up, and as a result of that, we're climbing with a higher ball velocity, with a higher launch angle. So we're climbing forever.
Yeah.
So that was not a good iron, actually, because we were climbing too far. So we had to adjust the trajectory and put it down to make a regular, normal trajectory.
Yeah, and to achieve the distances that you're looking for.
And so actually we achieve even more than what we were looking for, because we had to close a little bit the loft of those iron just to achieve a normal trajectory. And so by doing a little closer loft, we generate even more ball velocity, and we went even further. And that's how with the M2 iron, we have not only a long iron, but an iron that flies high, unlike most distance iron that have a tendency to fly low.
Yeah. So we hear this discussion at different times about they've de-lofted the iron so it's going further, right? And that's not entirely the truth. You de-lofted the iron to maximize the distance that you can pull from an exotic design, is what it comes down to.
Yeah, so I would say that that's the traditional approach, is you looking for distance and you close your loft.
Right.
And you pay all the price that are coming with that. No control around the green, low ball flight.
Yeah.
And we didn't want to do that. We wanted to create a great distance and a great trajectory together. And I think that with this speed pocket and this location of center of gravity, we were able to do that. And our angle of descent is steeper, and we're holding the green, even if the iron is extremely long.
Yeah. Well, that's a great story.
It was a big breakthrough for us to consider the M2 iron as a multifaceted aspect, rather than just trying to go after one side of the performance. It's trying to hit on all aspects of the performance.
So we've taken some of the things that we are learning in driver design and the complexity of the driver heads, and we're moving them into the iron faces. So we have iron faces now with driver face kind of technology, with thin faces that respond to the ball, and we have different kind of loft adjustments.
Yeah,
Yeah.
it is true that our technology are going back and forth. Our
Yeah,
iron
yeah.
team on one side, metal William team on the other side, and actually, when you look at for example, just the story of the Speed Pocket,
Right.
it started with the fairway rocket balls, and then he made it through the iron, and some of the technology that we also have on the face made their way from the metal wood and down to the irons, and vice versa. Sometimes some of the technologies start, for example, the flooded iron,
Yeah.
the flooded hosel here.
Yeah.
It's the way to save some weights and put it down. That started with the iron. And that technology actually was transferred to the metal wood
To the-
technology.
yeah.
So our new M2 Fairway and M2 Rescue are featuring
Yeah.
actually that technology. So they go back and forth.
Yeah.
Uh-huh.
Well, that's a great story. Thanks for spending your time with us.
Thank you, Russ.
And, we'll be looking for you next year.
Mm-hmm.
And, much success with TaylorMade.
Thank you very much.
It's a great brand. There's a lot of experience here. And it just keeps getting better every year, doesn't it?
Mm-hmm. Oh, yeah. Everything we've done so far, we carry it with us for the next product.
Very good. So this is Russ from DevotedGolfer.tv. Thanks for spending your time with us.